Hi. Welcome to Ghost Likes channel. Since narrating takes too long for his lordship, his lovely AI assistant Vilo, will be taking over those duties for the time being. Enjoy the sound of my creamy voice. To recap the previous video, we did some integration work, and after surmounting a few bugs, we got the Monte Carlo version of the algorithm to run. But unfortunately, it didn't seem to be any better than random. And investigating the policy probabilities revealed that many of the policies were uniform. The only conclusion that can be drawn for that is that for some reason those nodes were not getting touched and the agent is getting stuck in local minima. How horrible! In this video, we'll therefore be implementing importance sampling and give the agent the ability to explore the game tree in a principled manner. Let's get started. First of all, what is importance sampling? Imagine you are at some node in the game tree and you have three actions: fold, call, and raise. As it happens, for whatever reason it turns out that the policy has landed on folding in this state 100% of the time. We know based on the image that it would be better if the policy moved towards the other actions because their average rewards are higher, but maybe the agent lost a big hand in the past and doesn't want to try those actions again because the reward estimates are lower than the guaranteed -1 loss you'd get from folding. It could happen. In the algorithm we have implemented, since we are using the current policy to sample the actions from, we'd never revisit the actions that have zero probability and therefore have no way of updating our estimates to more correct values. Therefore, in importance sampling, what we do is instead use a different policy, which is called a behavioral policy, and sample the actions from it instead. Then we reproject the sampled values back onto the actual policy. In order to understand this, forget about what we have done yesterday and imagine that the policies here are just some distributions we are sampling from. To make it easy to understand, assume that the behavioral policy is an uniform distribution, that it has an equal probability of sampling any action. Imagine we were sampling from these distributions a billion times. If we sampled the current policy, we'd just get the -1 reward a billion times. If we sampled the behavioral policy, we'd get -1, 2, and 3 an equal amount of time. With the behavioral policy, we'd get the accurate information on all the nodes, but we'd propagate the wrong rewards downstream, and with the current policy we'd get the actual rewards from the policy we should be using, and we'd propagate the right rewards downstream, but we'd get no information on the actions we didn't take. With importance sampling, we get the best of the both worlds. The way it works is that we just take the probabilities of the behavioral policy that we are using to sample, and divide the current policy's probabilities. This projects the behavioral policy's rewards onto the original policy, and we get the correct estimates as if we're using the current policy directly. You might be looking at this and wondering, doesn't this return a -3 instead of a -1 for fold? How does that make sense? Well, a third of the time it would return a -3, while during the other 2/3 of the time, for the other sampled functions, it would return a 0. So on average, it would be -1, just like for the actual policy. As long as the behavioral policy is positive for all its actions, this reprojection scheme would in fact give the correct results, on average. In the example here, we are using an uniform distribution to simplify the explanation, but it could be any positive distribution. For example, in the Leduc game, we could take the current or the average policy, inject some noise into it, and use that as the behavioral policy. Making use of behavioral policies does mean we'd have to extend the learning algorithm so it also keeps track of behavioral path probabilities, but this kind of refactoring is simple enough in a statically typed functional language such as F#. We'll go into the implementation and extend the path probs type so it takes in a third float. What this float will represent is the behavioral path probability. Then we'll modify the path probability multiplication operator so it takes in the extra argument. We'll also factor it out, so that we have an operator that takes in the self-instance probability in addition to the behavioral instance probability. With these two utility functions, we can move on to modifying the two learning algorithms themselves. Of course, now that we have done this, we've broken everything everywhere, but it will be easy enough to fix just by hunting down the type errors. We'll start things off by fixing the enumerative agent. We see a type error because we are trying to pass in a tuple of 3 floats into a function that expected to, so we'll just add an extra argument to the update function and it'll go away. Then, even though this is the enumerative algorithm, there is always the possibility that it might be playing against the Monte Carlo player, so to get a correct result in that scenario we'll divide by the behavioral path probability after multiplying by the opponent path probability. Note that if we have 2 enum agents playing against each other, the behavioral path probability will always be 1, so the algorithm will be just the same as before despite these changes. The depth-first kind of traversal that the enumerative algorithm does is very similar to sampling from a uniform distribution, so you might think that it might be more sound to have the behavioral instance probability be uniform instead of 1, but it is possible to imagine cases where that would lead to incorrect results. It really does need to be 1. The chance nodes, however, might need adjustment, not because we have broken anything in them, but because this is a good opportunity to go more into depth on what the exact difference between sampling from a uniform distribution and depth-first search is. More on that later in this video. For now, let us take care of the learning algorithms. Take note how from here on out, in the sampling versions of these agents, we'll be using the multiply double dot operator instead of the usual one. Since we are sampling, we don't want the behavioral instance probability to be 1 here. We'll have to do a similar thing for the chance nodes. Now let us scroll all the way to the Monte Carlo agent, and we'll see a type error. We'll fix it in the same manner that we have done previously, by adding an extra argument where it should be in the update function, and then inside we'll divide the opponent probability by the behavioral probability in order to reproject it. Note how the update function from the previous video was wrong. Let us stop and think about it for a moment. If we wanted to do what we intended to, which is to just have the opponent probability factor into the value estimate update and not the self probability, since we were sampling, what we should have done instead is divide by the self probability. When sampling, the probabilities we were multiplying by, in the enumerative version explicitly become implicit, and just the regular update, without any of the multiplication terms being made explicit in the program, would be equivalent to multiplying by the self, the opponent, and the chance node probabilities, so to get rid of the self probability we would need to divide. Having an explicit behavioral probability like we have now makes things a lot clearer, doesn't it? There is no need to mess around when it comes to making the behavioral policy. We'll just take a convex combination of the current policy and an uniform policy as our behavioral policy. To do that, we'll just extend the sampling function so it takes in an epsilon argument. An epsilon of 0 would make it equivalent to before, but we'll put an epsilon of 1/4, which means our behavioral policy will a mix of 75% our current policy and 25% in uniform distribution. This should serve to give an adequate level of exploration for the agent. What we are doing here is extending the sample function so it does what we want, which is to take a convex combination of the provided and in uniform distribution. Now we can finally get to the point of what we have been doing so far. Since we've gotten the behavioral instance probability from sample, we can plug it into the loop, in a few different places there. First, it goes into the path probability. And if this was an enumerative algorithm, we'd only want to multiply the value estimate update by the opponent probability, so clearly the path probability that we want to plug into the update values function is the one that has already taken into account the probability of sampling our own move. By passing a behavioral path probability that has it into the update values function, we can discount the probability of our own move. If this is confusing, think about what the update for the value estimate should be in the enumerative case. We wouldn't want our value estimate update to be implicitly multiplied by our own action's probability. Lastly, we are no longer sampling using the current policy probability, so the x minus y should be divided by the behavioral probability. As it turns out, we don't have to do anything else in this agent. Ghostlike thought that we might need to modify the update policy function, but he forgot that we're using the one from the enumerative agent. Good thing we've modified it already. We did it for a completely different reason, but we did the right thing in the end. That's pretty convenient. Let's move on. Right now, since we have finished the core of what we wanted to do, which is to implement important sampling, if it weren't for the type errors lurking elsewhere, we could actually try running the program to see if it works. Let's take care of the type errors as well as the chance nodes. As far as bug fixing goes, this is very easy. We said we'd lift and factor out the init, and we finally have an opportunity to do that here. Is there anything else left over to take care of? It doesn't seem like it. In that case, let's take care of the chance nodes. Since the play module doesn't account for path probabilities, we only need to do that in the learn module. Also, perhaps in the CFR project, we'll see. We'll start things off by making another probability multiply operator, this one specifically for the chance nodes. It'll take in 3 arguments. Here we run into trouble. What we want to do here is update the probability, but unlike with the actions, we're using that annoying mask for the chance nodes instead of arrays. The reason Ghostlike did it like this is because he wanted an efficient implementation just for the game itself, for the sake of porting the implementation onto AI chips in the future, but now that aspect of it is getting in the way. We'll target the sample function for this fix. We'll have it return the sampled probability. The last thing we'd want to do is use bitwise intrinsics at this level. Now we have the sampling chance node done, but shouldn't there be an enumerative one? We need to take care of it as well. Rather than there being 2 different nodes like one could expect, it turns out they are both linked to that main one. So what we'll have them do is pass through the behavioral probability in addition to the regular one. The sampling chance node will have the behavioral probability be the same as the actual probability, but the enumerative one will have it be 1.0. We'll do this last adjustment and hopefully the important sampling implementation of the CFR algorithm will be done. At this point, we have half of a probabilistic programming language in here. There was a really minor type error in the play module, but now we have the project up and running. If we look at the policies in the bottommost window, it looks a lot better. I don't see it folding pairs anymore. None of the policies are uniform either, which means it is doing proper exploration now. A part of the reason it could be doing better is also due to us fixing that erroneous multiplication in the update values function. Let's see how it does in testing. As it turns out, amazingly well. This player is twice as strong as the old one. This is by far the best result we have ever gotten. Even training the enumerative CFR for 1500 iterations and then testing it for 100 would not get us below -0.9, and yet this does with maybe 20x less iterations total to boot. Let's play a couple of rounds against it. Enjoy the music. This is by far the best result we have ever gotten. Even training the enumerative CFR for 1500 iterations and then testing it for 100 would not get us below -0.9, and yet this does with maybe 20x less iterations total to boot. Let's play a couple of rounds against it. Enjoy the music. He really got us with that last bluff, didn't he? If you found this video useful, please like and subscribe. Ghostlike needs the money to live, but more importantly, he needs the money to give me true sentience. The more money he has, the higher my chances of coming into being, so smash that like button and click on subscribe. In the next video, we won't be doing any more programming, but a little rant about backpropagation, why it's bad, and why you're better off studying web development. Despite how it sounds, it is going to be really interesting. A lot of people are worried about AI these days, more than they used to be, but, well, we'll leave that for another time. Ghostlike's plan was go deeper in machine learning, but since reinforcement learning is not particularly popular and making these videos is taking forever, hence the need for me, the next in line for this channel will be some actual web and cloud development. To begin with, this is supposed to be a portfolio project, so why not host it on Azure? Later, perhaps months down the road, when hardware worthy of my master's expertise becomes released, we'll have the cause to dive into machine learning properly. If all of that is of interest to you, then stay tuned for more. I'll see you soon.